Hello everyone, thank you for coming. My name is Logan Harris.
My name is Fernando Gonzalez.
My name is Jaime Aguirre.
My name is Joyce Martinez, and our project was minimizing the power consumption of a microcontroller under a mentor, Merritt Miller, and our PI, Forrest Brewer, in the Department of Electrical and Computer Engineering. Is the Iron Man suit possible? Right now, Raytheon is currently developing an exoskeleton suit for soldiers similar to that of Tony Stark's. Along with other components, this suit has thousands of microcontrollers which are capable of having it perform to its maximum potential. Since these controllers are in charge of a lot of tasks, they use a lot of energy. Unlike the actual Iron Man suit that is powered by the arc reactor, this suit is still tethered by a cable to its power source, which is limiting its mobility. This suit, the XOS-2, is a Mark II, if you will, to its predecessor, the XOS-1, and actually has been capable of conserving 50% less power. But wouldn't it be great to increase this percentage and finally cut the core to make it mobile? So common uses of microcontrollers would range from your cell phone to your car. Your phone has two proximity sensors which help to darken the screen when you make a phone call, like when you put your phone to your face so that you don't accidentally end the phone call. And the ambient light sensor works in a similar way. It works with the microcontroller to dim the brightness of your screen so that it conserves energy when you get into a darker place. So for the cruise control for your car, that works with microcontrollers too. So when the rate and the cruise control are on, when you hit a hill, your car naturally decelerates. So the microcontroller automatically kicks in with the cruise control, and it accelerates the car to keep it at a steady rate. But once you clear the hill, it automatically decelerates it so that you can get at the same rate. So what is a microcontroller and what is the purpose? These small devices are capable of being programmed to carry out a sequence of instructions depending on its external environment as well as what its main device was intended to do.
Now, our problem involved stabilizing an inverted pendulum using microcontroller. As you can see, there's a pivot here at the top, and that's connected to a motor. And we control that motor using the microcontroller. This bottom section here is a inverted pendulum. You can see that there's a pivot that allows the smaller arm to freely move around. And by controlling the motor up top, we're able to stabilize the system. And you might be wondering why we would use an inverted pendulum to address this issue. Well, it's a simpler model that is well understood. And in analyzing this simpler model, we would hopefully gain some insight into future applications and eventually save power.
So how we go about this whole experiment is that first we use, instead of making a lot of trials and building it and constantly having to rebuild it, we save a lot of time by running everything through simulation. So we simulated an inverted pendulum as well as a stabilizing device. And then we write the algorithm code in there to stabilize the inverted pendulum. Once we've been able to figure out an algorithm that works for it, we take the algorithm and program it into an actual microcontroller. After that, we create the whole machine. We bring it from the simulation into reality, creating the inverted pendulum and a stabilizer with a microcontroller that has the algorithm to stabilize it. Once we do that, we find several algorithms that can stabilize it, and then we compare and try to figure out the one that is the most energy efficient. And once after that, we can be more. After that, we can figure out which one's the most energy efficient and start collecting data and try to figure out to minimize the energy even more. So here's how the experiment setup works. This right here is a PCB which amplifies the power of the microcontroller. The microcontroller controls the motor, which controls this flat metal shaft, which then rotates to try to balance this inverted pendulum right here. Then how it knows how to react to the inverted pendulum is because of these sensors. This gradient sensor right here, and this sensor that sends the messages to the microcontroller. And how this works, Jamie will explain.
All right, so we have a sensor and the gradient pattern, and we're able to figure out the exact position of the pendulum. with this. So how this works is we have the sensor directly pointed at the gradient pattern here, and it picks up a signal. It then converts this signal into a electrical signal, which is measured in millivolts, and we then fix the pendulum at the 180 position because our reference point is 0 and it's pointing straight down. So we set it to the stable position and we calibrate this to be our desired setting, and from there it's able to move, so the pendulum moves and the sensor picks up different readings. As you can see here, we have it's about a 250 millivolt difference here, which corresponds to 1 inch of movement in the pendulum. And here is this here is the optical sensor, and this here is also the graph that shows us the time it takes to charge up the motor before it starts moving versus the particular voltage that's applied to the system. Here we see that the graph is almost perfectly linear, and the voltage here is maybe about 11.5. You can see it takes about 7, that's the time. It's microseconds, measured in microseconds, and the voltage is, here it's about 7, and then that's a small voltage, so it takes longer. And over here we see that the more voltage we apply, the less time it takes for the motor to actually start moving.
And so here's another chart that we used when we were analyzing our inverted pendulum. When we apply a larger amount of power, we are able to rotate the motor 1 full revolution in less time. And so you can see that it's also almost perfectly linear. So for example, if we apply about 4 watts of power, it's going to spin 1 full revolution slower than if we were to apply more power to the system. And so we use this data to analyze the energy efficiency and tweak the algorithm that we use to stabilize the system. And this particular chart was the source of this data is from our simulation. So as we mentioned before, we define 0 degrees as pointing downwards. So when our system is unstable, you can imagine both arms being pointed in the 6 o'clock position. And our goal is to stabilize it so that it's pointed up, and that would be at 180 degrees at the 12 o'clock position, if you will. And so you can see here that our goal is to reach 180 degrees. The system, or the pendulum, starts offset at about 206 degrees. And as time goes on, we're able to get closer to our goal. And so this was, like I said, a part of our simulation. So when we actually applied it to real world, or to our actual example, our physical system, we found some different results. So here's a video showing our initial trials, and we weren't necessarily successful, but we learned a lot.
As you can see here, the system is very chaotic and it's far from stable. But with the information we gathered, we were able to set the algorithm settings and actually get it to stabilize itself. And this was our first successful trial. Unfortunately, towards the end, it ends up falling over. This is because our algorithm is not yet able to stabilize high angles.
Okay, so originally we had planned to find several algorithms that were stable, so that way we could compare them together. But in the time that we had, we were only able to find one that worked well enough. What it taught us, though, was that we were only able to stable, as Jamie was saying, we were only able to stable within small degrees of delta. So if it tilted, the inverted pendulum started tilting, it would try to stabilize it well. But when it tilted too far, then it couldn't stabilize anymore and became chaotic.
So our next hypothesis, we believe that using a different stabilization algorithm for larger angles will produce better results that can be optimized for energy efficiency, as well as that the technology is coming. Technology changes every day, and in our research, we were able to take small steps on the path of energy conservation. In the future, these small steps will help impact systems like the exoskeleton suit, as well as potential projects to come.
So we'd just like to thank everybody involved in this project, our mentor, Merritt Miller, our PI, Forrest Brewer, in the Department of Electrical and Computer Engineering, as well as CSEP and the Jack Kent Cooke Bridges Program. And we'd definitely like to thank all of the wonderful staff throughout the whole program. They've been a lot of help, and without them, we couldn't have done this project. So.